Have you ever wondered what the word astronomy really means? Not the technical definition you'd find in a textbook, but the quiet truth of it. The reason humans have always looked up and tried to make sense of the light scattered across the sky. Hello and welcome to the Sleepy Astronomer. This channel is all about slowing down, unwinding and drifting through the universe at a gentler pace. Whether you're lying in bed, relaxing on the sofa, or just letting the noise of the day fade away, you're in the right place. Where are you watching from tonight? I always find it fascinating to see where in the world people are listening from. All of us under the same sky, just at different corners of it. If you enjoy calm, factually accurate journeys like this one, a like and a subscribe really help the channel grow. And if you're already subscribed, thank you. It means a lot to have you here. I hope this video isn't so interesting that it keeps you awake, but if it does, at least you'll drift off a little wiser than before, maybe thinking about galaxies instead of tomorrow's to-do list. So, what is astronomy really? How did we come to understand the sky above us, and what does it reveal about our place in the universe? Astronomy isn't just about stars and planets. It's about curiosity, about noticing patterns in the night sky and realizing they tell stories that stretch across time. It began long before telescopes or equations, when early humans used the heavens to navigate, to mark seasons, and to make sense of their world. Over thousands of years, those quiet observations evolved into one of the most far-reaching sciences we know. In this video, we'll trace that story, from the first stargazers who mapped the motions of the heavens to the instruments that now reach far beyond our planet. We'll explore what light really is, and how it carries clues about distance, time, and even the chemistry of stars. You'll hear how we measure the universe's vast scale, how we study planets orbiting distant suns, and how we've learned that space itself is stretching and changing with time. We'll move through the lives of stars and how they're born, live and die, and how their remains become the building blocks for new worlds, including our own. We'll see how galaxies form, how gravity shapes the universe, and how every new telescope gives us another way to listen to the cosmos. By the end of this journey, astronomy will feel less like an abstract science, and more like a conversation between humanity and the universe, one that's been going on for as long as people have looked up. So settle in, let your thoughts slow down, and let's begin where all astronomy begins, under a dark, quiet sky, looking up and wondering what it all means. Long before the telescope, before glass lenses or written words, people were already studying the sky. The first astronomers had no instruments apart from their eyes, patience, and memory. Yet their observations shaped how humanity measured time, planted crops, and navigated oceans. For them, astronomy was not a science separated from daily life. It was survival written in starlight. Imagine standing in ancient Mesopotamia more than 4,000 years ago. The air is warm, the horizon flat, and the night sky endless. Each sunrise and sunset, each phase of the moon, was recorded by priests who watched from the ziggurats, tall temple towers built closer to the heavens. They marked the paths of planets across the sky and noticed that certain stars rose and set in predictable patterns. By comparing clay tablets over decades, they discovered that celestial rhythms could be used to forecast the flooding of rivers, the best times for sowing, and the cycles of the seasons. The Babylonians created some of the earliest star catalogues and divided the sky into constellations that became the foundation of the zodiac. Farther west, the ancient Egyptians were equally meticulous. They aligned their pyramids and temples with astonishing accuracy to the cardinal points of the compass. Every night, astronomer priests observed the stars that appeared just before dawn, the so-called decans, and used them to divide the night into equal parts, creating an early star clock. The annual rising of the bright star Sirius just before the sun signalled the coming flood of the Nile. That single observation synchronized agriculture, religion, and governance. Astronomy, geometry, and architecture were interwoven into one fabric of precision and faith. Across the Mediterranean, Greek thinkers began asking why the heavens behaved as they did. To them, the sky was a perfect and ordered system, one that could be explained through geometry. Around the 4th century BCE, Eudoxus of Cnidus designed the first mathematical model of the cosmos, using nested spheres to describe planetary motion. Later, Hipparchus refined these ideas and, through painstaking comparison of star positions, made one of the earliest scientific discoveries in history, the precession of the equinoxes. He noticed that the point where the sun crossed the celestial equator at spring gradually shifted westward along the ecliptic. In simple terms, Earth's axis wobbles slowly like a spinning top, completing one cycle roughly every 26,000 years. That insight revealed that the heavens were not entirely fixed but subtly changing. To the Greeks, the sky was also a vast laboratory of geometry. They measured angles between stars using sighting tubes and developed trigonometry to calculate distances on Earth by analogy with distances in the heavens. The meridian, an imaginary line running north to south through the zenith, the point directly overhead, became a reference for time and motion. By marking when the sun crossed that line, they defined local noon. With every new tool, astronomy became less mystical and more mathematical, though wonder was never entirely lost. Meanwhile, on the other side of the world, Polynesian navigators were turning the night sky into a map of the sea. Without compasses or charts, they memorized the rising and setting points of hundreds of stars, using them to steer canoes across thousands of kilometers of open ocean. Each island was linked to a unique pattern of star paths, swells, and cloud shapes. Their knowledge was passed orally from master navigators to apprentices, encoded in songs and stories that ensured it could never be forgotten. For them, astronomy was both art and instrument, a living science that guided whole civilizations between scattered worlds of the Pacific. At its heart, early astronomy everywhere served the same purpose: to bring order to the unpredictable. Calendars emerged as tools of coordination for crops, festivals, and taxation. The division of the year into months and days came directly from the cycles of the moon and sun. Eclipses, once feared as cosmic omens, became predictable once their patterns were recognized. By around the 5th century BCE, Babylonian astronomers could forecast lunar eclipses with surprising accuracy using records alone. Their tables of planetary motion laid the groundwork for later models that would echo through Greek, Islamic, and European traditions. Mythology accompanied observation, not as superstition but as a way of remembering. In cultures without writing, stories gave stars names and meaning, turning patterns into memory palaces. Orion was not merely a set of bright points, but a hunter whose position marked the change of seasons. The Pleiades, a small cluster easily visible to the naked eye, were often tied to agricultural cycles. When they rose before dawn, it was time to plant. When they vanished, it was time to harvest. These tales were mnemonic devices dressed as legends, allowing knowledge to persist for generations. The concept of the solstice, when the sun reaches its highest or lowest point in the sky, was recognized by many ancient peoples who built monuments aligned to these turning points. At Stonehenge in England and Nabta Playa in Egypt, massive stones still stand as silent calendars, catching the first rays of the solstitial sun. The equinox, when day and night are equal, held equal importance. It defined balance, a celestial checkpoint dividing the year into halves. Through such alignments, people turned the entire planet into an observatory, Even without written formulas, they achieved precision that astonishes modern archaeologists. They tracked the sun's path along the horizon, noted the phases of the moon, and understood the rhythm of the seasons long before formal science existed. In every culture, astronomy evolved from practical need to intellectual pursuit. Watching the sky meant more than predicting floods or guiding ships. It was humanity's first attempt to find order in the unknown. The early astronomers taught us that careful observation could turn mystery into understanding, and that patterns, once seen, could be trusted to repeat. Their records, carved in stone, written on clay, or remembered in story, became the first data set humanity ever collected. Each observation was a small rebellion against ignorance, proof that by paying attention we could decode the universe. Over time, that curiosity demanded more than naked eye observation. To map the heavens properly, the sky needed a coordinate system, a universal framework that could describe every star's position and motion. The moment humanity looked beyond storytelling and sought precision, astronomy crossed the line from art to science. And that need for order, for exact positions and repeatable measures, led directly to the next great step: learning how to locate the sky itself. The first step to understanding the sky is learning how to describe it. Without a shared map, every observation becomes a guess. The ancient astronomers understood this instinctively. They could point to a star, but to explain where that star was to someone on the other side of the world, they needed a system. Out of that need came the idea of the celestial sphere, an imaginary shell surrounding the Earth, on which all the stars appear to sit. It isn't real, of course, but it's one of the most useful illusions ever invented. From any point on the planet, you can imagine the sky as a vast globe turning slowly above your head, with the Earth's equator and poles projected outward onto it. The north and south celestial poles are simply the extensions of Earth's axis into space, and the celestial equator is the projection of our planet's equator onto that great dome. Every star can then be plotted somewhere on that sphere, fixed by coordinates that never change. To see how it moves, picture the heavens as a clock face in constant motion. Each day, the stars appear to rise in the east and set in the west, not because they move, but because Earth spins from west to east. That daily rotation gives us the illusion of a revolving sky. Over the course of a year, though, a slower change takes place. As Earth travels around the sun, the background of stars visible at night shifts gradually. The constellations you see in January are different from those in July because you're looking outward from a different side of our orbit. Not all star patterns are what people think they are. A constellation is an officially recognized area of the sky, a slice of that imaginary sphere. An asterism, on the other hand, is just a recognizable shape within or across constellations, like the Big Dipper inside Ursa Major, or the Summer Triangle formed by 3 stars from entirely different constellations. In 1928, the International Astronomical Union, or IAU, divided the sky into 88 official constellations. That decision turned centuries of folklore into something like a celestial grid, neat, measurable, and globally consistent. To specify a star's exact position, astronomers use 2 coordinates, right ascension and declination. Right ascension is like celestial longitude, measured eastward along the celestial equator. Declination is like celestial latitude, showing how far a star lies north or south of that equator. Together, they form the universal address system for the sky. If someone gives you those 2 numbers, you can point a telescope anywhere on Earth and know exactly where to look. For more immediate local viewing, say standing in your backyard, there's another coordinate system based on your own horizon. This one uses altitude and azimuth. Altitude measures how high an object appears above the horizon, while azimuth tells you its direction around the horizon, measured from north through east. Unlike right ascension and declination, these coordinates change constantly as Earth rotates. They're personal to you, a snapshot of your particular sky at one particular moment. Running diagonally across the celestial sphere is a path called the ecliptic. It's the apparent track the Sun follows across the sky over a year, traced by Earth's orbit. Because the planets lie roughly in the same plane, they all appear close to this line. The ecliptic defines the zodiac not as a mystical system but as a simple slice of geometry. It's the plane of our solar system projected onto the sky, a reminder that all the worlds we know share the same flat stage. One star stands apart as a nearly perfect anchor, Polaris, the North Star. It sits so close to the North Celestial Pole that it appears almost motionless while the rest of the sky spins around it. For northern navigators, Polaris is a compass frozen in place. Its height above the horizon even tells you your latitude. At the equator, it sits on the horizon. At the North Pole, it's directly overhead. For thousands of years, it's been the traveller's reassurance, a point of stillness in a moving world. But that steadiness isn't permanent. Over long spans of time, Earth's axis slowly wobbles like a top, a motion known as precession. This means the position of the celestial poles drifts in a slow circle, completing one full loop roughly every 26,000 years. When the Egyptians built the pyramids, the star Thuban, not Polaris, marked true north. A few thousand years from now, another star will take its place. The constellations we know today will shift subtly over millennia, like continents drifting across the map of the sky. Understanding precession also helps explain a subtle difference between two ways of measuring a day: solar time and sidereal time. A solar day, 24 hours, is the period it takes for the Sun to return to the same position in the sky. But because Earth moves along its orbit while it rotates, it has to spin a little more than once for the Sun to reappear at the same spot. A sidereal day, measured by the stars instead of the Sun, is about 4 minutes shorter. It represents one true rotation of Earth relative to the distant universe. To the casual observer, that difference goes unnoticed, but astronomers depend on it to predict when stars will rise and set. Without sidereal time, the clockwork of the heavens would never stay in sync. These overlapping systems, celestial, local and orbital, might seem abstract, but together they form the mental map that makes astronomy possible. They allow a single observation in one place to be shared, checked and verified anywhere else on Earth. That's the quiet beauty of it. The same coordinates that guide a mountaintop telescope also guide someone lying on a field, tracing patterns with their eyes. Every star, every planet, every flicker of light has its place, measurable and knowable, even if it lies thousands of light years away. By mapping the sky we see, we've built a bridge between the familiar and the infinite, turning what once seemed random into something almost comforting in its precision. And once you can locate the stars, the next question naturally follows. How do you capture their light and begin to understand what it's telling you? When you look up at the night sky, everything you see, every star, planet and glowing cloud, is nothing more than light. Every detail we know about the universe, from the temperature of a distant galaxy to the makeup of a star's atmosphere, comes from decoding that single messenger. Light is the language of the cosmos, and astronomy is the art of learning how to read it. Light can be thought of as both a wave and a particle. The particle form is called a photon, a tiny packet of energy that has no mass and always travels at the same speed. The speed of light, about 3/100,000 kilometers per second. Yet those photons can behave like ripples, spreading through space in waves. The length of those waves, called their wavelength, determines what kind of light they are. Long waves carry low energy, short waves carry high energy, and everything we see sits somewhere on that enormous spectrum. The portion visible to human eyes is surprisingly narrow. Stretch the entire electromagnetic spectrum across the width of Earth, and the colours we see would occupy less than the width of a coin. On one end of that spectrum are the long, lazy waves of radio light, each crest separated by meters or even kilometers. Moving upward in energy brings microwaves, then infrared light, the gentle heat radiating from warm objects. Pass through the visible colours from red to violet, and you reach ultraviolet light, then X-rays, and finally the shortest, most energetic gamma rays, with wavelengths smaller than the atoms they strike. Astronomers use all of these. Radio telescopes listen for enormous, slow whispers from cold gas clouds or spinning neutron stars. Infrared observatories peer through dust to see the birthplaces of stars. Ultraviolet and X-ray detectors reveal violent regions around black holes, while gamma-ray telescopes catch brief flashes from the universe's most extreme explosions. What we call the night sky is just the narrow slice our eyes evolved to notice. Even within that visible range, light has a rich inner structure. When it passes through a prism, it spreads into a spectrum, a rainbow of colours arranged by wavelength. That spread is more than pretty, it's diagnostic. Hotter objects shine more strongly at shorter, bluer wavelengths, while cooler ones emit more at longer, redder wavelengths. Every object with a temperature above absolute zero emits light according to this rule. A perfect black body in physics terms radiates energy across all wavelengths in a smooth curve that peaks at a specific colour. The sun, for instance, glows brightest in the green part of the spectrum, but we perceive it as white because it emits strongly across the visible range. A cooler star, like Betelgeuse, radiates more red light and looks warm and coppery to our eyes. When astronomers plot that curve, they can determine a star's surface temperature without ever touching it. A blue star might blaze at 30,000 degrees Celsius, while a red one might glow gently at 3,000. The physics of blackbody radiation is so consistent that, by measuring the colour of light, we can read a cosmic thermometer from across light years. But the real magic of light appears when you look closer at the spectrum and find that it isn't perfectly smooth. Scattered across it are narrow, dark gaps and bright spikes. These are absorption lines and emission lines, the fingerprints of atoms. When light passes through a gas, certain wavelengths are absorbed by the atoms within it, because electrons inside those atoms can only jump between specific energy levels. Each element has its own set of permitted jumps, so the pattern of missing wavelengths identifies exactly which elements are present. The same process in reverse creates emission lines. When excited atoms drop back down to lower energy states, they release photons at those same precise wavelengths. Every star, nebula and galaxy carries a unique pattern of these lines. By spreading their light into a spectrum, astronomers can read composition, temperature, pressure, and even magnetic fields. It's forensic science on a universal scale. Helium, for instance, was discovered in the sun's spectrum before it was ever found on Earth. Even now, when new molecules are detected in distant exoplanet atmospheres, it's through these same delicate imprints. Light also carries motion. When a luminous object moves toward or away from us, the waves it emits are stretched or squeezed, a phenomenon called the Doppler effect. The same principle makes an ambulance siren rise and fall in pitch as it passes. In light, this stretching or compression shifts the colour. When an object moves away, its light is stretched toward longer, redder wavelengths, a redshift. When it approaches, the light is compressed toward shorter, bluer wavelengths, a blue shift. This simple shift reveals astonishing things. The speed of orbiting stars can be measured just by the slight wobble of their spectral lines. Entire galaxies can be clocked as they recede through space. It was through redshift measurements that astronomers discovered the universe itself is expanding, that galaxies aren't just moving, but that space between them is stretching. Every distant cluster of stars carries its own motion written into its light, a gentle smearing of colour that tells us where it's heading and how fast. Our eyes, remarkable as they are, can sense only a fraction of all this information. They detect light in 3 broad bands, red, green and blue, but can't distinguish subtle spectral details. Nor can they see beyond the visible range. The night sky may appear dark to us, but to instruments tuned to radio, infrared or X-rays, it blazes with structure. What we call empty space is often crowded with radiation invisible to our senses. Even so, human vision is a masterpiece of evolution, fine-tuned to the sun's spectrum and to the window of transparency in Earth's atmosphere. If we could see only infrared or ultraviolet light, the air would block most of it, and the world around us would look opaque. Our eyes were built for the narrow view that life on this planet allows. Telescopes extend that view, acting as translators for forms of light we can't perceive directly. The story of light is also the story of curiosity, of finding that something as ordinary as colour hides the physics of the universe. From a single beam, we can tell what an object is made of, how hot it is, how far away it lies, and how fast it's moving. All of it encoded in the gentle vibration of energy that started its journey perhaps billions of years ago and ends in the back of your eye. Every photon is a traveller carrying a message from the moment it was born. Some began their journey in the heart of stars, others in the violent collision of galaxies, or the fading afterglow of the Big Bang itself. They cross unimaginable distances, dodging dust and gas, until at last they reach a detector, or simply your gaze on a clear night. And to truly read these ancient messages, to catch more of them, and to study them in finer detail, you need something our eyes were never built for, a better way to gather light. A telescope is, at its core, a simple idea. Collect as much light as possible and bring it into focus. That's all it does, but in doing so it changes everything. Our eyes can only gather a small trickle of light, limited by the size of the pupil. A telescope replaces that tiny opening with a far larger one, allowing us to collect fainter signals from far greater distances. The first working telescopes appeared in the early 1700s, though legends of magnifying tubes go back further. Galileo didn't invent the telescope, but he was the first to turn one toward the heavens and record what he saw. His refracting telescope, or refractor, used curved glass lenses to bend light to a focus. It revealed the rough surface of the moon, the phases of Venus, the moons of Jupiter, and the strange ears of Saturn, which he couldn't quite resolve as rings. The view was crude by modern standards, but revolutionary all the same. A refractor works by bending or refracting light through glass, but light of different colours bends by slightly different amounts, producing a rainbow blur around bright objects called chromatic aberration. Early lens makers tried to correct it by pairing lenses of different glass types, but it was never fully eliminated. Large lenses also had practical problems. They were heavy, expensive, and could only be supported at the edges, causing distortions under their own weight. The solution came from Isaac Newton, who replaced the front lens with a curved mirror. A mirror reflects all wavelengths equally, avoiding colour distortion. The design became known as the reflector. Newton's version used a small secondary mirror to redirect the focused light to the side, so observers didn't block the incoming beam. Reflectors could be built much larger than refractors, since a mirror can be supported from behind. This breakthrough changed the scale of astronomy forever. Over the centuries, telescope designs diversified. The Newtonian layout, simple, open and inexpensive, remains popular for amateur observers. The Cassegrain design, with light bouncing between a large primary mirror and a small convex secondary, folds the optical path back through a hole in the primary, creating a compact but long focus system. Many large observatories use variations of this setup. A refinement called the Ritchie-Chrétien design corrects optical distortions over wide fields of view and became the standard for professional instruments, including the Hubble Space Telescope. When you look at a telescope, the most important number isn't its magnification, as people often assume. The real key is the aperture, the diameter of its main lens or mirror. The aperture determines how much light the telescope can gather and how sharp its view will be. A bigger aperture collects more photons, revealing fainter objects, and also increases the resolution, the ability to distinguish fine details. Resolution depends on both aperture size and wavelength, but a good rule of thumb is that doubling the aperture roughly doubles the sharpness. Magnification, meanwhile, is just the ratio between the telescope's focal length and the eyepieces. You can make almost any telescope produce high magnification, but that doesn't mean you'll see more. If the air above you is turbulent, details smear and shimmer no matter how powerful your optics are. Astronomers call this effect seeing, the distortion caused by Earth's atmosphere. Even on the clearest night, air currents blur starlight, limiting sharpness. Another factor, transparency, describes how clear and moisture-free the air is. High mountain observatories are built where seeing is steady and transparency is high, above dust, humidity, and most of the weather. For centuries, astronomers recorded their observations by sketching, but the arrival of photography transformed everything. By the late 1800s, glass photographic plates could capture light faint enough to be invisible to the human eye. Long exposures accumulated photons over hours, revealing distant galaxies and nebulas in exquisite detail. These plates turned astronomy into a quantitative science. A permanent record could be measured, compared, and reanalyzed. Then, in the late 20th century, a new technology took over, the charge-coupled device, or CCD. Unlike film, which fades and must be developed, a CCD converts incoming light directly into electronic signals. Each pixel counts photons with extraordinary efficiency, detecting over 90% of the light that strikes it, compared with only a few percent for photographic plates. CCDs are linear, precise, and sensitive across a wide range of wavelengths. With them, telescopes could finally see not only fainter objects but also measure them accurately. Still, the atmosphere remained a problem. Even at the best sites, starlight twinkles as moving air bends it unpredictably. To correct this, astronomers developed adaptive optics, a technology that senses those distortions in real time and flexes a thin mirror many times per second to cancel them out. It's a bit like noise-cancelling headphones, but for light. With adaptive optics, ground-based telescopes can achieve near space-like sharpness, bringing distant galaxies and even details on exoplanets into focus. Of course, not all astronomy relies on visible light. Some telescopes are built to detect other parts of the electromagnetic spectrum. Radio telescopes, for instance, use huge metal dishes to collect long wavelength radio waves. They often work in arrays, linking multiple dishes across vast distances. This technique, called interferometry, combines the signals to act as a single, giant telescope, with a resolution far exceeding any single dish. The Very Large Array in New Mexico and the Global Event Horizon Telescope Network use this method to study cosmic phenomena, even imaging the shadow of a black hole. Each part of the spectrum reveals something different. Infrared telescopes peer through coal dust to study star formation. X-ray observatories hunt for high-energy events like supernova remnants or matter spiraling into black holes. gamma-ray detectors trace the most violent explosions in the cosmos. Because Earth's atmosphere blocks much of this radiation, many telescopes must be launched above it. Space telescopes have given us the clearest, most uninterrupted views of the universe. The Hubble Space Telescope, orbiting since 1990, has produced images so sharp that they redefined our sense of scale. The James Webb Space Telescope, operating primarily in infrared, sees through clouds of dust to capture the faint light of the first galaxies. Free from atmospheric turbulence, these instruments turn the cosmos into an open book. Telescopes today are far more than optical tubes. They're integrated systems of mirrors, sensors, computers, and precision mechanics, all working in harmony to gather light that may have travelled billions of years to reach us. Even a small backyard telescope, though humble by comparison, operates on the same principles as the largest observatories on Earth or in orbit. Both are extensions of human vision, tools that amplify our curiosity. From a simple lens in Galileo's hand to arrays spanning continents, every improvement has been about one thing: collecting more light and sharpening what it reveals. Through telescopes, we don't just see farther, we see deeper, uncovering detail within detail, until the night sky becomes not a mystery, but a map of time. And with that light now gathered, the next challenge arises: to measure the distances it has travelled and learn just how vast the universe truly is. When you look up at the stars, distance is impossible to judge by sight alone. The night sky flattens everything into one glittering dome, making nearby stars and faraway suns appear side by side. To the unaided eye, Orion's belt looks like a tight cluster, yet its 3 stars lie at vastly different distances, one a few hundred light-years away, another more than 1,000. Measuring how far things really are was one of the hardest challenges astronomy ever faced. The first and most direct method is called parallax. It relies on simple geometry. Hold your finger in front of your face and close one eye, then the other. Your finger seems to jump against the background. That tiny shift is parallax, the change in apparent position when viewed from 2 different vantage points. Astronomers apply the same principle to the stars, using Earth's orbit as the baseline. When we look at a nearby star in January and then again in July, the Earth has moved about 300 million kilometers across its orbit, and the star appears to shift slightly against the background of more distant stars. By measuring that angle and knowing the size of Earth's orbit, the distance can be calculated with trigonometric precision. For nearby stars, parallax is the gold standard, a clean geometric measurement with no assumptions about the star itself. But it's limited. The shift is minuscule. Even for the closest stars, it's less than 1 arc-second, about the width of a coin seen from several kilometers away. Before space-based instruments, detecting it required decades of careful photography. Today, satellites like Hipparcos and Gaia have refined these measurements to astonishing accuracy, mapping billions of stars and anchoring the entire cosmic distance ladder. Beyond the reach of parallax, astronomers need brighter beacons, stars whose intrinsic power can be guessed from their behaviour. These are called standard candles, objects whose true brightness or luminosity is known well enough that their apparent brightness reveals their distance. It's the same principle as judging how far away a street lamp is by how bright it looks, provided you know how powerful the bulb really is. Among the most famous of these candles are Cepheid variable stars. These are unstable, pulsating suns that rhythmically swell and contract, changing brightness in a predictable cycle. In the early 1900s, astronomer Henrietta Swan Leavitt studied hundreds of Cepheids in the Magellanic Clouds and discovered a precise relationship. The longer a Cepheid takes to pulse, the brighter it truly is. That link between period and luminosity meant that by timing the rhythm of a Cepheid's flicker, its distance could be calculated. Leavitt's discovery turned variable stars into the rulers of the universe, stretching our cosmic measuring tape far beyond the range of parallax. Later, astronomers added another kind of standard candle, a particular type of exploding star known as a Type 1a supernova. These occur when a white dwarf in a binary system steals matter from its companion until it reaches a critical mass and detonates in a thermonuclear flash. Because all these explosions happen under nearly identical conditions, their peak brightness is remarkably consistent. A Type Ia supernova shines billions of times brighter than the Sun, making it visible across vast distances. By comparing its observed brightness to the known standard, astronomers can gauge how far away its host galaxy lies. These supernovae became the ultimate yardsticks, used to measure distances halfway across the observable universe. Each rung on this so-called cosmic distance ladder depends on the one below it. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae in turn calibrate entire galaxies. It's a chain of trust, refined step by step until the scale of the universe begins to emerge. Yet it's never perfect. Each step introduces small uncertainties, errors in brightness estimates, variations in dust absorption, or differences in calibration. Those small errors can multiply as the ladder extends, so astronomers constantly revise and cross-check their measurements. Even today, slight disagreements between methods, such as those based on the cosmic microwave background versus local Cepheid distances, fuel debates about the exact rate of cosmic expansion. When Edwin Hubble and Georges Lemaitre compared galaxy distances to their redshifts in the 1920s, they discovered something extraordinary. The farther away a galaxy is, the faster it appears to be receding. The relationship between distance and recession velocity became known as the Hubble-Lemaitre law. Each galaxy's light is stretched by the expansion of space, its spectral lines shifted toward the red. The slope of that relationship defines the expansion rate of the universe, the Hubble constant. Measuring it precisely remains one of astronomy's greatest ongoing quests. Because light takes time to travel, distance and time in astronomy are inseparable. When you look at the moon, you see it as it was just over 1 second ago. Sunlight shows us the sun as it was 8 minutes in the past. The light from the nearest star, Proxima Centauri, left over 4 years ago. The farther we look, the older the light. Galaxies millions or billions of light-years away show us snapshots from deep cosmic history. Astronomers call this look-back time, the idea that a telescope is also a time machine. Every image is a layered record of events long finished, the light only now arriving to tell their story. By stacking these observations at different distances, we can reconstruct the universe's history, galaxies forming, merging and evolving, stars being born and dying, structures growing under gravity's pull. It's a bit like watching a movie in reverse, with each frame farther back in time than the last. To make all this work, astronomers use something called the distance modulus, a simple mathematical relationship between a star's apparent brightness and its intrinsic luminosity. It allows distances to be expressed on a logarithmic scale, compact and manageable even when numbers stretch into the billions. Though you rarely see the equation outside of textbooks, it underpins almost every map of the cosmos. Calibration is an ongoing art. Instruments drift, filters differ, and cosmic dust obscures light unevenly across wavelengths. Astronomers spend enormous effort correcting for these effects, often using nearby stars or galaxies as cross-checks. Even so, small uncertainties linger. When you're measuring something measured in billions of light-years, a difference of just a few % still spans unimaginable space. Despite the complexity, the goal remains beautifully simple: to turn brightness into distance and distance into history. With every refinement, our map of the universe grows more precise. What began with the width of Earth's orbit has expanded to encompass the entire observable cosmos. Every star's parallax, every pulsating Cepheid, and every distant supernova contributes to a single grand measurement, the scale of reality itself. And within those distances, invisible but constant, lies the quiet force that holds it all together. Gravity, the unseen thread that keeps the universe in motion. If light is the universe's storyteller, gravity is its choreographer. Everything that moves, spins, or orbits does so under gravity's quiet direction. It doesn't shout like radiation or sparkle like stars. It simply bends the path of everything around it, shaping the cosmos with an invisible hand. The first person to describe that cosmic dance in detail was Johannes Kepler in the early 1700s. Kepler inherited an enormous pile of data from his mentor Tycho Brahe. Decades of meticulous observations of planetary positions, all made without a telescope. For years he wrestled with the numbers, trying to make them fit the perfect circles the ancients had always assumed the planets followed, but they didn't. No matter how he twisted the geometry, Mars refused to behave. Eventually Kepler realized the truth. Planets move in ellipses, not circles. An ellipse is a stretched circle, an orbit with two focal points instead of one, with the Sun sitting off-center at one of them. That was Kepler's first law. His second law described how a line drawn between the Sun and a planet sweeps out equal areas and equal times. In plain terms, planets move faster when they're closer to the Sun and slower when they're farther away. His third law linked the size of a planet's orbit to its orbital period. The greater the distance, the longer the year. These three rules transformed our understanding of motion from a geometric curiosity into a predictable system. A few decades later, Isaac Newton revealed why those rules worked. His law of universal gravitation proposed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of their distance. It was a simple equation, but it united heaven and earth. The same force that makes an apple fall also keeps the moon in orbit. Gravity wasn't a special power of the planets. It was a universal property of matter itself. From Newton's insight came a new understanding of orbital motion. A planet in orbit is in a delicate balance between the pull of gravity and the tendency to move in a straight line. The result is continuous free fall. The planet is forever falling toward the Sun, but its sideways motion carries it around instead of into it. The same principle explains the Moon's path around Earth and the International Space Station's steady glide above us. Everything in orbit is falling, just perpetually missing. The strength of that balance can be described through energy. Every orbiting body has both kinetic energy, from its motion, and potential energy, from the gravitational pull trying to reel it in. Change one, and the other just compensate. This trade-off creates stable paths, unless something comes along to disturb them. The minimum speed needed to break free of an object's gravity entirely is called the escape velocity. For Earth, it's about 11 kilometers per second. A rocket that reaches that speed can leave our planet for good. Slower, and it will eventually fall back. Escape velocity depends only on mass and distance, so massive worlds and compact stars have higher thresholds. A neutron star's escape velocity is so extreme that light itself cannot climb out, forming what we know as a black hole. Closer to home, gravity's reach creates tides. The Moon pulls more strongly on the side of Earth nearest to it, stretching the ocean slightly and creating bulges of water that move as Earth rotates. The Sun adds its own tug, and together they shape the rhythm of the tides. A quiet reminder that celestial mechanics touch even the most familiar waves. In more extreme environments, tides become destructive. The gravity gradient near a massive planet or black hole can stretch and tear apart smaller bodies, producing luminous streams of debris. When multiple objects orbit the same body, as in our solar system, their gravitational influences interact in subtle ways. Sometimes these interactions create harmony, orbital resonances, where bodies tug on each other in rhythmic patterns that keep the system stable. For instance, Pluto and Neptune are locked in a 2-to-3 resonance. Pluto completes 2 orbits around the Sun for every 3 of Neptune's, ensuring their paths never collide. Jupiter's moons, Io, Europa, and Ganymede also share a resonance, their motions synchronized like gears in a clock. Resonances can amplify stability, but they can also cause chaos when small shifts push systems out of balance. Planetary migration is another product of these interactions. Early in the solar system's history, giant planets like Jupiter and Saturn likely moved from their birthplaces, rearranging the smaller bodies around them. Evidence of this comes from patterns in the asteroid belt and the captured outer moons of the gas giants. Beyond our system, exoplanet studies have revealed worlds that orbit perilously close to their stars, hot Jupiters that probably formed far away and drifted inward. Gravity's influence is slow but inexorable, capable of reshaping entire planetary systems over millions of years. Not all motion is so orderly. In regions crowded with stars, such as galactic centers, close encounters can eject stars entirely from their galaxies or send them spiraling inward towards supermassive black holes. Even within the relative calm of the solar system, gravitational nudges from passing bodies accumulate, creating long-term unpredictability. Mathematicians call this chaos, not in the sense of randomness, but in extreme sensitivity to initial conditions. A tiny shift in position today might lead to a completely different path 10 million years from now. Still, amid that apparent chaos, gravity fosters structure on every scale. It gathers gas into clouds, clouds into stars, and stars into galaxies. Over billions of years, it sculpts the cosmic web, drawing filaments of matter together like dew forming on a spider's silk. Yet some of gravity's behavior doesn't quite add up. When astronomers measure how fast stars orbit within galaxies, the outer stars move faster than expected, as if extra mass were hiding in the dark. These measurements create what's known as a rotation curve, a graph of orbital speed versus distance from the galactic center. Instead of tapering off, as Newtonian physics predicts, the curve stays flat, implying the presence of unseen matter. This missing mass is what we now call dark matter, invisible, detectable only through its gravitational pull. Gravity, simple as it sounds, remains mysterious. Einstein refined it further in his general theory of relativity, showing that gravity isn't really a force but the curvature of space-time itself. Matter tells space how to curve, and space tells matter how to move. Yet even this elegant picture leaves puzzles unsolved. The nature of dark matter, the cause of cosmic expansion, the ultimate fate of gravitational systems over infinite time. For all its complexities, the essence of gravity is balance, a continuous negotiation between attraction and motion. It's the reason moons stay loyal to their planets, planets to their stars, and stars to the spiral arms of galaxies. The same law that governs a falling apple binds entire galaxies together across the universe, and under its steady influence, gravity does something even more beautiful. It takes diffuse clouds of gas and dust drifting through space and compacts them until they ignite, creating stars, the brilliant engines that light up the cosmos. Every star that has ever shone, from the faintest red ember to the blinding blue giant, began its life in the same way, as part of a cold, quiet cloud adrift in space. These immense structures, called molecular clouds, are the nurseries of the cosmos. They're made mostly of hydrogen, with traces of helium and small amounts of heavier elements. Some stretch across hundreds of light years, containing enough material to form millions of suns. Yet they're so tenuous that a cubic centimetre of space holds fewer particles than the best vacuum humans can create. Seen through an optical telescope, these clouds appear as dark patches blotting out the stars behind them, but in infrared light they glow faintly, revealing intricate filaments, knots, and whorls. The most famous examples, the Orion Nebula, the Eagle Nebula's pillars of creation, the Tarantula Nebula, are only the visible fringes of far larger complexes. Inside these vast regions, gravity quietly competes with pressure. The gas wants to spread, but wherever density increases slightly, gravity gains a small advantage, pulling more matter inward and deepening the imbalance. Star formation usually needs a push to begin. That trigger can be anything: the shock wave from a nearby supernova, the passage of one cloud through another, or the spiral-arm density waves that sweep through galaxies. Whatever the cause, once a patch of gas becomes dense enough, its own gravity takes over. The collapse accelerates, breaking the cloud into fragments that will each form one or more stars. Astronomers call these collapsing clumps cores. As they shrink, they spin faster, conserving angular momentum, the same reason a figure skater spins quicker when pulling in their arms. The spinning motion causes infalling gas to flatten into a rotating disk around the forming star. At the centre of each collapsing core, temperature and pressure climb. The embryonic object at its heart is known as a protostar, a hot, dense sphere still gathering mass from its surroundings. Material from the surrounding accretion disk spirals inward, heating as it falls. This process can continue for hundreds of thousands of years, during which the protostar is shrouded by dust that hides it from visible view. Only infrared telescopes can peer through that obscuring material to witness the earlier stages of birth. Even as gas continues to rain down, the young star fights back. Magnetic fields funnel some of the infalling matter into twin jets that blast outward along the star's poles, clearing away excess material. These jets can stretch for light years, carving cavities through the parent cloud and lighting up shock fronts where they slam into the interstellar medium. The combination of accretion and outflow is a kind of cosmic breathing, the cloud collapsing inward even as the newborn star exhales, energy and motion back into space. Over time, the inflow slows and the surrounding disk begins to thin. The protostar grows hotter and denser until its core temperature approaches 10 million degrees Celsius. At that threshold, hydrogen nuclei begin to fuse into helium, releasing enormous energy. This marks the start of true stellar life, the moment gravity's inward pull and the pressure from nuclear fusion reach equilibrium. The star stops collapsing and settles into stable adulthood, shining steadily as a main sequence star. The main sequence is the long, stable phase that defines most of a star's existence. The position a star occupies on that sequence depends on one thing above all: its mass. Mass determines temperature, luminosity, and lifespan. A small star, with a fraction of the Sun's mass, burns its fuel slowly and can shine for hundreds of billions of years, longer than the current age of the universe. A massive blue star, 10 or 20 times the Sun's mass, consumes its hydrogen in only a few million years before collapsing and exploding in a violent supernova. This simple rule, mass decides fate, is one of the most elegant truths in astronomy. It's also why the night sky contains such variety. Most stars, about 3/4 of them, are small, dim red dwarfs that will live quiet, uneventful lives. The rest span a wide range of sizes and colours, from orange K-type stars slightly cooler than the Sun, to massive O-type stars so bright that they outshine thousands of suns combined. The balance between gravity and fusion sets each one's rhythm, a long equilibrium that can last billions of years. In a young star cluster, these differences are easy to see. The more massive stars form first and dominate the scene, blazing intensely in blue-white light. Around them, countless smaller stars are still cocooned in dust, their light visible only in infrared. Over time, radiation from the big stars clears away the gas that birthed them, halting further formation and leaving behind an open cluster, a glittering collection of siblings slowly drifting apart. Star formation is an incredibly inefficient process. In a typical molecular cloud, less than 1% of the gas ever becomes stars. The rest is dispersed by winds, radiation, and supernova blasts. Yet those violent outflows play an important role. They enrich the remaining gas with heavier elements forged in earlier generations of stars. Each new wave of star birth therefore begins with slightly more complex material, gradually seeding the galaxy with the ingredients for planets and life. Modern telescopes equipped with infrared detectors and millimeter wave arrays have given astronomers a front row seat to this process. The Atacama Large Millimeter/Submillimeter Array in Chile, perched high in the desert where the air is thin and dry, can detect the faint warmth of dust grains as they swirl within disks around newborn stars. Some of these disks already show clear signs of sculpting, rings and gaps where planets may be forming. In other regions, networks of filaments stretch across hundreds of light years, each strand a potential cradle for future suns. Because visible light can't escape the densest parts of these clouds, infrared and radio observations have become essential. At those longer wavelengths, astronomers can see through the obscuring dust and watch stars in their infancy. The glow of warm gas, the outflowing jets, and the ripples of shock waves tell the story of stellar birth in exquisite detail. What's remarkable is how universal the process seems to be. Whether in a small dwarf galaxy or a grand spiral like our Milky Way, wherever cold gas gathers, gravity begins its patient work. Star formation links the scales of the universe, from microscopic dust grains colliding in a disk to the rise of whole stellar populations that light up galaxies. And while the process takes millions of years, the result is simple and profound. Gravity turns darkness into light. Within every molecular cloud, invisible and silent, countless futures are forming. Stars that will one day host planets, planets that may one day host oceans, and perhaps eyes that will look back toward the stars and wonder how it all began. The cycle of creation doesn't end there, of course. Each star that's born will eventually run out of fuel, and its fate will depend on the mass it started with. Some will fade quietly, others will die in spectacular explosions that scatter their elements back into space, ready to build new worlds. The story of star birth naturally leads to its counterpart, the story of how stars die and how their endings shape everything that follows. Every star lives on borrowed time. The light that fills the night sky is the visible part of a long and intricate process, a balancing act between gravity pulling inward and nuclear fusion pushing outward. When that balance falters, a star begins to change, transforming itself and, in doing so, reshaping the universe around it. Stellar death is never truly an ending. It's the engine that builds everything else. For a star like the Sun, the story unfolds slowly. For billions of years, it fuses hydrogen into helium at its core, steadily converting a small fraction of its mass into energy. But eventually, the hydrogen in the central region becomes scarce. When fusion can no longer sustain the outward pressure, gravity begins to gain the upper hand. The core contracts and heats, while the outer layers expand and cool, turning the star into a red giant. In that swollen phase, the radius can reach 100 times its original size. If Earth survives the expansion, the the sun will appear so large in the sky that it would dominate the horizon. Inside that giant, something remarkable happens. As the core contracts, its temperature climbs until it reaches about 100 million degrees Celsius. Under such heat, helium nuclei begin to fuse into carbon and oxygen, the next step in the cosmic recipe. For a while, balance is restored, and the star burns helium steadily in a smaller, hotter core. But helium too is limited. When it runs out, the process repeats on a smaller scale. The core contracts again, the outer layers puff out further, and the star becomes unstable. Eventually the sun will shed its outer layers into space, forming an expanding shell of glowing gas known as a planetary nebula, a name that dates back to early telescopes when these faint disks looked planet-like. The exposed core left behind will shrink into a white dwarf, a dense, Earth-sized remnant supported not by fusion, but by quantum pressure from its electrons. A single teaspoon of white dwarf material would weigh several tons. Though it no longer generates new energy, it will glow for billions of years as it slowly cools and fades into darkness. For stars more massive than the Sun, the ending is far less peaceful. Their greater weight means greater pressure and higher temperatures in the core, allowing fusion to continue beyond helium. Carbon becomes neon, oxygen becomes silicon, and eventually iron forms at the centre. But iron is a dead end for fusion. It cannot release energy through fusing or splitting. Once an iron core forms, gravity has no opposing force left. The collapse is catastrophic. In less than a second, the core implodes under its own gravity, reaching densities so extreme that protons and electrons merge into neutrons. The star's outer layers crash inward, rebound off the compressed core and explode outward in a supernova, a titanic blast that can outshine an entire galaxy. For a few weeks, the light from a single dying star can rival billions of others combined. The collapsed core may stabilize as a neutron star, an object no wider than a city but containing more mass than the Sun. A neutron star is so dense that a sugar cube of its material would outweigh Mount Everest. Its surface gravity is hundreds of billions of times stronger than Earth's, and its magnetic fields can accelerate particles to near light speed. Some spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses, pulsars, ticking out their rotations with incredible precision. If the collapsing core exceeds roughly 3 times the mass of the Sun, even neutrons cannot withstand the pressure. Gravity overwhelms every known force, crushing matter into a point of infinite density. The boundary around that point from which not even light can escape is called the event horizon, the defining feature of a black hole. Beyond it, space and time themselves are curved so sharply that all paths lead inward. Black holes are not cosmic vacuum cleaners as often imagined. From a distance, their gravity is no stronger than that of any other object of equal mass. Yet up close, they are nature's most extreme laboratories, places where our understanding of physics begins to break down. Supernovae and their remnants do far more than destroy. They forge and distribute the elements that make the universe complex. Inside stars, fusion builds elements up to iron, but heavier elements, gold, platinum, uranium, require something more violent. When neutron stars collide, their combined gravitational and magnetic chaos triggers a brief but spectacular explosion known as a kilonova. In those fleeting moments, enormous quantities of nucleosynthesis occur, creating the heaviest elements and flinging them into space. Every atom of gold in a wedding ring was likely born in one of these collisions. The debris from such events enriches the surrounding gas clouds, ensuring that the next generation of stars and planets forms with a richer chemistry. Over billions of years, this slow accumulation of elements transformed the early universe from a simple mix of hydrogen and helium into the diverse carbon-rich cosmos we inhabit today. When you trace the origins of the atoms in your body, most come from the death throes of long-vanished stars. In a very literal sense, every living thing is made from stellar ash. Astronomers can still read these histories in the light of stellar remnants. Nucleosynthesis, the process by which stars create new atomic nuclei, leaves signatures in spectra that reveal not only what elements were made, but where and under what conditions. Neutron stars tell us how matter behaves at densities that can't be replicated on Earth. Supernova remnants show how shock waves mix and distribute material through galaxies. Even white dwarfs preserve ancient records of how stars of different masses evolved billions of years ago. Though these remnants seem lifeless, they are among the most scientifically active places in the cosmos. Observations of pulsars have tested the limits of relativity. Measurements of supernova-like curves have refined the cosmic distance scale. Black holes, once only theoretical, have now been imaged directly, their shadows captured by networks of radio telescopes spanning the planet. Each of these objects, born from destruction, continues to illuminate the laws that govern everything. In the grand cycle of the universe, stars are both creators and recyclers. They begin as clouds of hydrogen, burn through stages of fusion, and then return enriched material to space. Every generation of stars builds upon the legacy of the last. The heavy elements that form planets, oceans, and life itself owe their existence to ancient stellar deaths. Even the calcium in our bones and the iron in our blood were forged in stars that exploded long before the sun was born. The next time you see a bright star, consider it not as a distant decoration, but as a living forge, a factory turning matter into energy, and energy back into matter. Every shining point in the sky is a temporary balance between gravity's pull and fusion's push, destined to one day give back its substance to the universe. The light you see tonight began as a nuclear reaction deep in a heart of plasma, and may someday return as the dust that forms another world, perhaps one much like our own. The evolution of stars is the story of transformation written in light and matter, beginnings leading to endings, and endings giving rise to everything else. To understand that cycle more personally, we need only look at the star we know best, the one that sustains our home and shapes every moment of our existence, the Sun. Every solar system begins with a star, and ours is no exception. The Sun dominates everything. Its gravity holds the planets in orbit, and its light powers nearly every process on Earth. It accounts for more than 99% of the solar system's total mass, a colossal sphere of plasma almost 1.5 million kilometers wide. Inside its core, hydrogen atoms fuse into helium, releasing energy that takes thousands of years to work its way to the surface and just 8 minutes to travel to Earth. The Sun's structure is layered. Deep within lies the fusion core, surrounded by the radiative zone where energy drifts outward as light. Beyond that, convection currents carry heat toward the surface, creating a seething pattern of granules that constantly bubble and fade. The visible surface, or photosphere, glows at about 5,800 degrees Celsius, the soft yellow we see from Earth. Above it lie the chromosphere and corona, tenuous outer layers that flare to millions of degrees, far hotter than the surface itself. That mystery still puzzles scientists today. The Sun is not quiet. Magnetic fields twist and snap, driving flares and eruptions that hurl charged particles into space. These particles form the solar wind, a continuous stream of plasma flowing outward in all directions. The Sun's influence extends far beyond the planets, creating a vast bubble known as the heliosphere. which acts as a shield against much of the galaxy's cosmic radiation. When the solar wind interacts with a planet's magnetic field, it produces shimmering auroras, curtains of light that ripple near the poles of Earth, Jupiter, and Saturn. Starting from the Sun, the first world you reach is Mercury, a cratered rock scorched by sunlight on one side and frozen on the other. It has no atmosphere to carry heat, and its surface has barely changed for billions of years. Venus follows, Earth's near twin in size but opposite in temperament. Its thick carbon dioxide atmosphere traps heat so effectively that surface temperatures soar above 400 degrees Celsius, hot enough to melt lead. The pressure is crushing, and clouds of sulfuric acid drift through its skies. Earth sits third comfortably within the Sun's habitable zone, the narrow region where liquid water can exist on the surface. It's a delicate balance, a protective magnetic field, a moderate greenhouse effect, and abundant water all combine to make it a haven for life. The Moon stabilizes Earth's tilt, preventing wild climatic swings and producing the tides that have shaped coastal ecosystems for billions of years. From every perspective, temperature, chemistry, orbit, and protection, Earth occupies a sweet spot of improbable stability. Next comes Mars, a smaller, colder world whose red hue comes from iron oxide dust. Once it had flowing rivers and lakes, and perhaps even an ocean in its northern hemisphere. Today, it's a desert, its atmosphere thin and unable to retain warmth. But beneath the dust lies ice, and robotic explorers have found evidence of water that once carved valleys and filled craters. Mars remains a frozen memory of what Earth might have been, or could become. Between Mars and Jupiter lies the asteroid belt, a vast region filled with rocky debris left over from the solar system's formation. The total mass of all those asteroids combined is less than that of the Moon, but they're rich in history. Some are metallic cores of failed planets, others are primitive, carbon-rich remnants containing water and organic molecules. The belt marks the boundary between the inner rocky worlds and the giant planets beyond. Jupiter is the solar system's monarch, more massive than all the other planets combined. Composed mostly of hydrogen and helium, it has no solid surface, just layers of gas growing denser with depth. Its atmosphere churns with colossal storms, including the Great Red Spot, a hurricane large enough to swallow Earth. Around Jupiter orbits a miniature solar system of its own, with more than 90 moons. Among them, 4 stand out. Io, the most volcanic body anywhere, is constantly reshaped by tides from Jupiter's gravity. Europa hides a global ocean beneath its icy crust, where life might exist in the warmth of undersea vents. Ganymede, the largest moon in the solar system, has its own magnetic field, while Callisto, heavily cratered and ancient, is like a time capsule from the solar system's early years. Beyond Jupiter, Saturn drifts through space adorned with its magnificent rings, billions of icy particles ranging from dust to mountain-sized chunks. They're surprisingly thin, only a few tens of meters thick in places, and might be remnants of a shattered moon. Saturn itself is light enough to float on water, though finding a bathtub big enough would be an engineering challenge. Its moons are equally fascinating. Titan, with a dense nitrogen atmosphere and lakes of liquid methane, is the only moon known to have stable surface liquids, and Enceladus, a small icy world, shoots geysers of water vapour into space from an underground ocean. Farther out still lies Uranus, a pale green ice giant tipped on its side, rolling around the sun like a barrel. Its odd tilt likely resulted from a massive collision long ago. The atmosphere is laced with methane, giving it its colour, and faint rings encircle the planet. Neptune, the outermost major planet, is smaller but more dynamic, with supersonic winds and deep blue hues. its largest moon, Triton, orbits backward, a captured object from the outer solar system. Beyond Neptune's orbit lies the Kuiper Belt, a region of icy worlds and frozen debris extending billions of kilometers into space. Pluto resides here, along with other dwarf planets like Haumea and Eris. The Kuiper Belt is the solar system's frozen frontier, a relic from its formation 4.5 billion years ago. Even farther out, perhaps 2 light-years away, lies the Oort cloud, a vast spherical swarm of icy bodies that marks the Sun's outermost gravitational boundary. It's from this distant reservoir that long-period comets occasionally fall inward, lighting up the inner solar system for a few brief weeks before returning to the deep freeze. The solar system, viewed as a whole, is a layered structure of contrasts: small, dense worlds near the Sun, giants made of gas and ice beyond, and a halo of debris marking the limits of the Sun's reach. Yet despite these differences, everything here shares a common origin, all formed from the same rotating disk of gas and dust that surrounded the newborn Sun. Over time, lighter materials drifted outward, heavier elements stayed near the centre, and the system we know took shape, orderly but dynamic, ancient yet alive with motion. Earth, nestled among these worlds, stands out not for its position but for its balance. Its protective magnetosphere, generated by a molten iron core, shields the surface from harmful solar radiation. Its atmosphere contains just the right mix of gases to trap warmth without overheating. Its oceans regulate temperature, while plate tectonics recycle carbon and shape continents. No other known world maintains such a harmonious equilibrium. Every planet and moon contributes a piece to this grand story. Together they show how one system can host deserts, oceans, volcanoes, ice, storms, and calm. The solar system isn't merely our address in space, it's a blueprint for how nature builds and experiments. And among the asteroids, comets, and icy leftovers, the oldest materials of all still orbit quietly, preserving the history of how it all began. Those small, silent wanderers are the time capsules of creation, reminders of the system's youth and the clues to everything that followed. In the grand architecture of the solar system, the smallest worlds often carry the biggest secrets. Asteroids, comets, and meteors are fragments left over from the dawn of planetary formation, leftovers that never joined a planet, frozen in time for billions of years. They are the fossils of the solar system, silent witnesses to its birth and evolution. Asteroids are the rocky debris of creation, orbiting mainly between Mars and Jupiter in what we call the asteroid belt. They range from tiny pebbles to worlds hundreds of kilometers across. Most are irregularly shaped, cratered, and scarred from countless collisions. Their compositions vary widely. Some are metallic, the exposed cores of ancient protoplanets stripped of their outer layers. Others are rich in carbon, dark and primitive, containing water-bearing minerals and complex organic molecules. These carbonaceous asteroids are especially intriguing because they preserve the chemistry of the early solar system almost unchanged. Astronomers classify asteroids by how they reflect sunlight, a property known as albedo. Bright, stony asteroids reflect more light, darker ones absorb it. This reflectivity, combined with colour and spectra, allows scientists to infer what each asteroid is made of without ever touching it. Space missions like Japan's Hayabusa and NASA's OSIRI-SREX have gone further, bringing samples back to Earth for direct analysis. The grains they returned are older than any rock on our planet, untouched since before Earth itself existed. While asteroids are rocky, comets are icy. They spend most of their time in the deep freeze of the outer solar system, far beyond the planets, until something disturbs their orbits and sends them inward toward the Sun. As a comet approaches, sunlight warms its surface, causing its ice to vaporize and release gas and dust. This creates the characteristic coma, a glowing envelope surrounding the nucleus, and the beautiful tails that stretch for millions of kilometers through space. The gas tail always points directly away from the Sun, pushed by the solar wind, while the dust tail curves gently along the comet's path. Comets are often described as dirty snowballs, though in truth they're more like snowy dirt, mixtures of ice, rock, and organic compounds. When they pass close to the Sun, they shed enormous amounts of material, leaving behind trails that Earth sometimes intersects. When that happens, we see meteor showers, streaks of light as tiny cometary particles burn up in our atmosphere. The terms can be confusing, so it helps to keep the hierarchy clear. A meteoroid is a small fragment of rock or metal travelling through space. When it enters Earth's atmosphere and burns due to friction, it becomes a meteor, the fleeting streak of light often called a shooting star. If any part of it survives the fiery plunge and lands on the ground, that remnant is a meteorite. Each stage tells part of the same story, the passage of cosmic debris from orbit to atmosphere to Earth itself. Every meteorite that reaches the ground is a messenger from another world. Some come from asteroids, others, incredibly, from the Moon or Mars, blasted free by ancient impacts. Their chemical fingerprints reveal the diversity of materials that went into building the planets. Some meteorites contain chondrules, tiny glassy beads that formed in the solar nebula over 4.5 billion years ago. Others carry traces of water and amino acids, hinting that impacts long ago may have delivered key ingredients for life to the young Earth. Impacts have shaped planetary history in dramatic ways. Craters mark the scars of that process everywhere we look. The Moon's pocked face, Mercury's battered plains, the basins of Mars. Even Earth, with its erosion and plate tectonics, bears evidence of colossal strikes. 66 million years ago, a 10-kilometer wide asteroid slammed into what is now Mexico's Yucatan Peninsula, triggering global fires, tsunamis, and climate collapse. That single event wiped out most of the dinosaurs and cleared the stage for mammals, and eventually humans, to rise. Not every impact is catastrophic, but the potential remains. Near-Earth objects, or NEOS, are asteroids or comets whose orbits bring them close to our planet's path. Most are harmless and regularly monitored, but even a small one could cause significant damage if it struck in the wrong place. The explosion of a 20-meter object over Tunguska, Siberia, in 1908 flattened forests for hundreds of square kilometers, a bolide, as astronomers called such an atmospheric detonation. For this reason, modern astronomy includes a quiet but serious discipline: planetary defense. Around the world, telescopes continuously survey the skies, tracking NEOs and refining their orbits. Space agencies maintain catalogues of potential hazards and simulate possible impact scenarios. If a future asteroid were found on a collision course, deflection would be the goal, not destruction. The simplest methods involve nudging the object slightly years in advance, using a kinetic impactor, a gravitational tug from a nearby spacecraft, or, in extreme cases, focused energy from sunlight or lasers. The key is early detection. A small adjustment far away is easier than a desperate maneuver at the last moment. NASA's DART mission, which successfully altered the orbit of a small asteroid in 2022, proved that such techniques work in practice. It was humanity's first test of planetary defense, a reassuring step in our growing ability to safeguard the world from the same cosmic forces that once reshaped it. Despite their potential for danger, these small bodies are invaluable. They are time capsules, preserving the raw ingredients of planets and the chemistry of the early solar nebula. By studying them, astronomers can reconstruct the solar system's formation with remarkable precision. Missions like Rosetta, which orbited and landed on a comet, and Lucy, now en route to study the Trojan asteroids of Jupiter, continue that exploration. Each object tells a slightly different version of the same origin story. In their own way, asteroids and comets remind us that the solar system is still active, still evolving. Dust trails drift, collisions occur, and new craters form, slow-motion echoes of the chaos that once filled this region. They also remind us that Earth is not separate from the cosmos, but part of its ongoing experiment. Every meteor streaking through the night sky is a tiny fragment of that story, briefly burning bright before returning to dust. And beyond these icy wanderers, beyond the scattered stones of our own solar system, there are countless other stars surrounded by their own debris, other systems, other worlds, and perhaps other beginnings waiting to be discovered. For most of human history, planets meant the few that orbit our sun, the familiar dots of light that wandered among the stars. It wasn't until the late 20th century that astronomers found the first planet around another star, and once they did, the floodgates opened. Today, thousands of exoplanets, planets beyond our solar system, are known, and the number keeps rising. They come in every imaginable variety. Worlds heavier than Jupiter hugging their stars, Earth-sized planets orbiting cool red dwarfs, and others so bizarre they defy neat classification. Each one reminds us that the solar system isn't a template, but just one possibility among billions. Detecting these distant worlds is a delicate art. The planets themselves are dim compared to the stars they orbit, often billions of times fainter. Directly imaging them is like trying to spot a firefly fluttering beside a lighthouse from hundreds of kilometers away. Most of the time, astronomers must rely on indirect evidence, tiny effects that betray a planet's presence. One of the most powerful of these techniques is the transit method. When a planet passes in front of its star from our point of view, it blocks a small fraction of the starlight. This produces a slight, regular dip in brightness that can be recorded as a light curve, a graph showing the star's brightness over time. Each time the planet crosses again, the same pattern repeats. From the shape and timing of that curve, astronomers can infer the planet's size, its orbital period, and even hints about its atmosphere. The amount of light blocked, known as the transit depth, reveals how big the planet is relative to its star. Transits are wonderfully precise, but depend entirely on geometry. The planet's orbit must be aligned just right with our line of sight. For every system that shows transits, there are dozens whose planets remain invisible simply because their orbits are tilted at the wrong angle. To complement the method, astronomers use another approach called the radial velocity technique. This method relies on the gentle gravitational tug that a planet exerts on its star. As the planet orbits, the star moves slightly too, wobbling around the shared centre of mass. That motion causes the star's light to shift in wavelength, alternately toward the blue when it moves toward us, and toward the red when it moves away, a result of the Doppler effect. Measuring these tiny shifts allows astronomers to determine the planet's minimum mass and orbital period. By combining radial velocity with transit data, both the size and density of a planet can be determined, revealing whether it's gaseous like Jupiter or rocky like Earth. Both techniques require extraordinary sensitivity. The wobble caused by an Earth-like planet on a Sun-like star is only about 10 centimeters per second, slower than a person walking. Detecting such faint signals demands instruments of incredible stability and high signal-to-noise ratios, meaning the planet's subtle signature must rise above the random fluctuations of starlight and instrument noise. Advances in spectrographs and long-term monitoring have made this possible, turning what was once science fiction into daily routine. A few exoplanets have been captured directly through direct imaging, though only under special conditions. These tend to be large young planets orbiting far from their stars, glowing faintly with leftover heat from formation. Even then, astronomers must use coronagraphs, optical masks that block the star's glare, and sophisticated processing to separate the planet's light from the surrounding brilliance. While rare, such images are profoundly striking. Actual photons from alien worlds, not just inferred signals. Beyond finding planets, scientists want to know what their atmospheres are made of. The key lies in spectroscopy, splitting the light into its constituent colours. When a planet transits, some of the starlight filters through its atmosphere. Molecules there absorb specific wavelengths, leaving telltale fingerprints in the spectrum. This is called transmission spectroscopy. It can reveal the presence of gases like water vapour, methane, carbon dioxide, or sodium. When a planet moves behind its star, astronomers can also measure the combined light before and after the eclipse. The difference gives the planet's emission spectrum, showing how much heat it radiates. These techniques have already yielded extraordinary insights. Astronomers have detected scorching skies rich in sodium, high-altitude clouds of silicate glass, and even hints of water vapour on temperate worlds orbiting small stars. None of these observations yet confirm life, but they demonstrate that atmospheric chemistry is as diverse as the planets themselves. The dream, of course, is to one day detect biosignatures, patterns of gases like oxygen or methane that could only exist in combination if replenished by living processes. However, the concept of habitability is more complex than the simple idea of a habitable zone. That phrase refers to the region around a star where temperatures would allow liquid water to exist on a planet's surface. It's a useful guideline but not a guarantee. A planet too small might lose its atmosphere. One without a magnetic field could be stripped bare by stellar winds. Even planets slightly farther out might remain warm if they have thick atmospheres or subsurface oceans, like Europa or Enceladus in our own solar system. True habitability depends on a web of factors: chemistry, magnetism, rotation, and chance. Biases also shape what we find. The first exoplanets discovered were mostly hot Jupiters, massive gas giants orbiting scorchingly close to their stars. They were easiest to detect because their size and tight orbits produced large, frequent signals. Smaller, Earth-like worlds take longer to reveal themselves. It's only with missions like Kepler, TESS, and now the James Webb Space Telescope that astronomers have begun to find rocky planets within more temperate zones. Yet even these discoveries are subject to selection effects. We can only see what our instruments are tuned to notice. The galaxy likely holds countless worlds our technology cannot yet detect. As the data grows, patterns begin to emerge. Planetary systems are incredibly varied, some with multiple close-packed worlds, others with tilted orbits or eccentric paths. Many stars host compact families of planets, with sizes between Earth and Neptune, a type of world missing from our own solar system entirely. These findings challenge old theories and force new ones, showing that nature is far more creative than our imagination. The study of exoplanets sits at a beautiful intersection of precision and wonder. Each discovery is a triumph of measurement: tiny dips in brightness, subtle shifts in starlight, painstakingly confirmed. But behind the numbers lies something deeply human: the realization that our sun is one among hundreds of billions, and that planets are not rare jewels but common outcomes of star formation. The more we look, the more inevitable it seems that the universe teems with worlds. And though our telescopes can't yet see the landscapes of those distant planets, we can already begin to sense their diversity: skies of methane and clouds of metal, oceans of lava, and frozen plains beneath red suns. Each detection adds another verse to the cosmic story of how stars and planets organize themselves into systems. And when we look at those countless points of light now, it's impossible not to wonder, how many of them are home to cities of stars surrounded by their own family of worlds? Every star in the night sky is part of something vastly larger, a galaxy, a collection of billions of stars bound together by gravity, drifting through space like glowing islands in a cosmic ocean. Our own Milky Way is just one of perhaps 2 trillion such islands scattered across the observable universe. From afar, each galaxy seems serene, but up close, they are dynamic, restless places where matter circulates, stars are born and die, and invisible forces shape everything. Galaxies come in a remarkable variety of shapes and sizes, but most fall into 3 main categories. Spiral galaxies, like our Milky Way, are graceful disks with sweeping arms that wind outward from a bright central bulge. Their flattened form is the result of rotation over billions of years. Gas and dust settled into a spinning plane, forming stars that trace its elegant structure. The arms aren't rigid. They're regions of higher density where star formation happens more readily, glowing with the blue light of young, hot stars. Elliptical galaxies are very different, large, smooth, and featureless, often shaped like stretched spheres or rugby balls. They contain mostly old stars and very little gas or dust, the raw material for new ones. The younger stellar generations have long since faded, leaving these galaxies with a soft reddish glow. Irregular galaxies are the rebels of the group, chaotic, lopsided, often the result of gravitational encounters or mergers that tore their structures apart. Some are small and clumpy, others are distorted versions of spirals mid-collision. Regardless of shape, every galaxy is a kind of ecosystem. Gas clouds condense into stars. Those stars live their lives and eventually return much of their material to space through winds and supernovae. That recycled gas then cools, collapses, and forms new stars, a continuous cycle of creation and renewal. But it's not an endless loop. Eventually, galaxies can exhaust their fuel or lose it through violent outflows. The processes that regulate this cycle are collectively known as feedback, the way a galaxy responds to its own energy output. Feedback comes in many forms. When massive stars die, their explosions send shockwaves through the surrounding gas, heating it and preventing it from collapsing again right away. Supermassive black holes in galactic centers add another layer. As gas falls toward them, it releases tremendous amounts of energy, sometimes outshining the entire galaxy. These luminous centers are called active galactic nuclei, or AGN. The radiation and jets from AGN can sweep gas out of the host galaxy, halting star formation for millions of years. This suppression of star birth is known as quenching. Some galaxies flicker between active and quiet states, alternating between bursts of star formation and long periods of calm. Our Milky Way sits somewhere in the middle, active enough to form new stars but not so energetic that it disrupts itself. The Sun is part of one of its spiral arms, orbiting the galactic center roughly every 200 million years. In that core lies a black hole about 4 million times the mass of the Sun. It's dormant by cosmic standards, quietly influencing the orbits of nearby stars rather than blazing as an AGN. For all their brilliance, galaxies hide a mystery that changed physics. In the 1970s, astronomer Vera Rubin and her collaborators measured how fast stars moved in the outer regions of spiral galaxies. According to Newtonian gravity, the farther from the centre you go, the slower the orbital speed should be, just as planets farther from the Sun move more slowly. But that wasn't what she found. The stars on the outskirts were moving just as fast as those near the centre. The rotation curve, a graph of speed versus distance stayed flat instead of declining. The only explanation that fit the data was that most of the mass wasn't visible. Something unseen was providing the extra gravity needed to hold the fast-moving stars in place. This unseen substance became known as dark matter. Dark, not because it's mysterious in tone, but because it doesn't emit, absorb, or reflect light. It interacts gravitationally, and that's how we know it's there. Today, every measurement of galaxies and galaxy clusters reinforces its presence. Roughly 85% of the matter in the universe is dark matter, yet no one knows what it's made of. Dark matter forms enormous halos around galaxies, invisible scaffolds that keep them bound. Without it, galaxies as we know them wouldn't exist. Their rotation would fling their stars into space. It also shapes the universe on larger scales, creating the seeds for structure in the first place. Early in cosmic history, slightly denser regions of dark matter pulled in gas, forming the first galaxies. The visible universe, in a sense, is just the luminous frosting on a vast invisible framework. Galaxies don't live in isolation. They gather in groups and clusters bound by shared gravity. The Milky Way belongs to the local group, a small cluster containing about 50 galaxies, including our neighbour Andromeda. Clusters can contain hundreds or thousands of galaxies embedded in hot gas that glows in X-rays. These clusters are themselves connected by filaments of dark matter and galaxies, forming a vast network known as the cosmic web, a structure that spans billions of light years. Between the filaments lie immense voids, nearly empty regions where few galaxies reside. Galactic interactions are common, even graceful in their violence. When galaxies pass close to one another, their mutual gravity distorts their shapes, pulling out long tidal tails of stars and gas. Collisions don't often involve stars hitting stars. The distances between them are too vast, but the gravitational turbulence can trigger waves of star formation. Over time, mergers can turn two spirals into a single elliptical. The stellar orbit scrambled into a new, smoother configuration. The Milky Way and Andromeda are on course to merge about 4 billion years from now, forming a new, larger galaxy that astronomers have already nicknamed Milkdromeda. Inside galaxies, the story of structure and evolution is one of balance. Gravity gathers matter into clouds, feedback disperses it, star formation uses up gas, stellar deaths return it. Collisions build larger systems even as internal forces strive to maintain equilibrium. On the grandest scales, the same balance repeats: attraction and expansion, collapse and dispersal, order and chaos, all woven into the same cosmic rhythm. When astronomers look deep into space, they're also looking back in time. The most distant galaxies we can see are faint and irregular, still in the process of forming. As time passes, these building blocks merge and mature, evolving into the grand spirals and ellipticals we see nearby. The light from those distant structures has travelled for billions of years, carrying with it a record of how galaxies grow, interact and fade. Each galaxy is a story of countless stars, but taken together, they form a single, vast narrative, one that stretches from the first clumps of matter after the Big Bang to the intricate web of structure we see today. If you could step back far enough to see it all at once, the universe would appear as a glowing network, filaments of light tracing an invisible skeleton of dark matter. And from that immense web, the next question naturally arises. What is the universe itself doing? Expanding, stretching and changing on the grandest scale imaginable. When astronomers look at distant galaxies, they notice something astonishing. Almost all of them are moving away. The farther a galaxy lies, the faster it seems to recede. This isn't because galaxies are speeding through space like shrapnel from an explosion. It's because space itself is stretching. The universe isn't expanding into anything, it's the very fabric of distance that grows, carrying galaxies along like raisins in a rising loaf of bread. This discovery reshaped our understanding of the cosmos. In the early 1920s, Edwin Hubble and Georges Lemaître noticed that the light from distant galaxies was shifted toward the red end of the spectrum, a result of the same Doppler effect that makes a siren's pitch drop as it moves away. This redshift revealed that galaxies weren't just scattered randomly. They were all receding, and the farther away they were, the greater their velocity. Space itself was expanding uniformly, stretching the wavelengths of light travelling through it. Astronomers describe this expansion using something called the scale factor, a measure of how distances between galaxies change with time. When the scale factor doubles, every separation between galaxies doubles too. It's as if the coordinate grid of the universe is being continually rescaled, while each galaxy stays fixed on its local patch. The galaxies themselves don't expand, nor do atoms or solar systems. The effect only becomes noticeable across immense cosmic distances. If we run that expansion backward in time, all those galaxies converge to a single, much denser state. The universe must once have been smaller, hotter, and brighter. So hot, in fact, that atoms couldn't exist. For hundreds of thousands of years after the Big Bang, the universe was an opaque fog of plasma, where light couldn't travel far before scattering off free electrons. As the universe expanded and cooled, protons and electrons finally combined to form neutral hydrogen. Suddenly light could move freely. That ancient light, released when the universe was about 380,000 years old, is still around today, stretched by cosmic expansion into the faint microwave glow that fills all of space. This glow is called the cosmic microwave background, or CMB. It's the oldest light we can see, a fossil imprint of the universe's infancy. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, who were puzzled by a persistent hiss in their radio antenna, the CMB turned out to be the afterglow of creation itself. It comes from every direction with almost perfect uniformity, a temperature of about 2.73 Kelvin above absolute zero, but with subtle variations only a few parts in 100,000. Those tiny fluctuations are incredibly important. They mark the seeds of all later structure. Imagine the early universe as a nearly smooth ocean of matter and radiation with gentle ripples. Where the density was slightly higher, gravity pulled in more material, eventually forming galaxies and clusters. Where it was slightly lower, matter drained away, leaving cosmic voids. This CMB is a snapshot of those first ripples, the blueprint for everything that followed. By mapping its temperature variations in exquisite detail, missions like COBE, WMAP, and Planck have revealed the universe's age, composition, and curvature with remarkable precision. The CMB also carries the imprint of sound. In the dense plasma of the young universe, gravity tried to compress matter, while radiation pressure pushed back, creating vast waves, literal acoustic oscillations that rippled through the cosmic medium. These waves froze when the universe became transparent, leaving a faint pattern in the distribution of galaxies today. Even now, the spacing of galaxy clusters echoes those primordial vibrations. The universe, in a sense, still hums with the memory of its first notes. Over billions of years, those ripples grew into the cosmic web we see now. Dark matter provided the gravitational scaffolding, while normal matter fell into its potential wells, cooling and forming stars and galaxies. The large-scale structure of the universe, its filaments, clusters and voids, is the grown-up version of those faint patterns traced in the CMB. For a long time, astronomers assumed that this expansion, while continuing, must be slowing down under the pull of gravity. The combined mass of all galaxies and dark matter should have been gradually decelerating the cosmic growth. Then, at the end of the 20th century, came another surprise. Two teams studying distant Type Ia supernovae found that those explosions were dimmer than expected, meaning the galaxies hosting them were farther away than the standard model predicted. The expansion of the universe wasn't slowing down at all, it was speeding up. Something, some unknown influence, was pushing the universe apart faster and faster. That mysterious phenomenon became known as dark energy. It accounts for nearly 70% of the universe's total energy content, yet its nature remains completely elusive. It doesn't behave like matter or radiation. It appears to be a property of space itself, an intrinsic tendency for expansion. One way to picture it is that as the universe grows, more space is created, and with it, more dark energy, a self-reinforcing cycle. Its effect dominates on the larger scales, overwhelming the mutual attraction of galaxies and clusters. In billions of years, the cosmic web will stretch so much that distant galaxies will fade beyond the reach of our telescopes, leaving only the nearest members of our local group visible. The universe will continue expanding forever, cooling and dimming as it does. Though dark energy remains one of the great enigmas of modern physics, its fingerprints are unmistakable. By combining observations of supernovae, the CMB, and galaxy clustering, astronomers can trace the universe's expansion history in detail. The evidence consistently points to an accelerating cosmos, a universe not static, not collapsing, but forever stretching. This idea can feel unsettling, yet there's a quiet elegance to it. The same expansion that began with the Big Bang continues now, not as an explosion, but as a gentle unfolding. Every photon of light we see from the distant past has been stretched, cooled, and carried along by that expansion. The night sky itself is a record of space growing beneath our gaze. When we look at the CMB, we're literally seeing the oldest light in existence, the first afterglow of creation, still washing over us more than 13 billion years later. It's astonishing to think that this faint microwave hiss, invisible to our eyes but present everywhere, contains the entire early history of the cosmos, its age, its contents, even its geometry. From the steady expansion that spreads galaxies apart to the first light that still whispers across space, the universe tells a story written not in motion but in vibration, a cosmic resonance that began long ago and still echoes today. Beyond light itself, the universe has other ways of speaking, not through radiation, but through ripples in space and time. Over a century ago, Albert Einstein proposed a daring idea, that gravity isn't a force pulling on objects, but a bending of space and time itself. When massive objects move suddenly, colliding, collapsing, or spinning together, they should send ripples through the very fabric of space-time, waves that stretch and squeeze everything they pass through. He called them gravitational waves. Einstein himself doubted they would ever be detected. They were far too faint, he thought, the distortions so tiny they would be swallowed by noise. For decades the concept remained theoretical, an elegant consequence of general relativity with no practical way to prove it. But the universe, as always, had other plans. To understand what gravitational waves are, imagine tossing a stone into a calm pond. The ripples that spread outward are like gravitational waves, not moving through the water's surface, but of the surface itself. When two massive objects such as black holes or neutron stars orbit each other, they stir the fabric of space-time in a similar way. These waves travel at the speed of light, carrying information not about what an object looks like, but about how it moves and what it is made of. Detecting them required an instrument of extraordinary precision. The solution came in the form of an interferometer, a device that splits a laser beam into two perpendicular paths, sends them bouncing off mirrors kilometers apart and then recombines them. If a gravitational wave passes through, it stretches one arm of the interferometer ever so slightly while compressing the other, altering the pattern of interference between the two beams. The change is minute, smaller than 1,000th the diameter of a proton, but measurable. The laser interferometer, Gravitational Wave Observatory, better known as LIGO, operates two such detectors in the United States, one in Washington state and one in Louisiana. Each has two 4-kilometer-long arms housed in vacuum tunnels so straight you could fire a laser from one end to the other without hitting the walls. For years, these instruments listened in silence. Then, on September 14, 2015, a faint rising tone appeared in the data, a brief chirp lasting just 0.2 of a second. It was the unmistakable signature of two black holes spiraling together and merging more than 1 billion light-years away. That tiny tremor confirmed Einstein's prediction and opened a completely new way of observing the universe. Until then, astronomy had relied entirely on light and its kin: radio waves, X-rays, gamma rays. Gravitational waves offered something different, a direct way to sense motion and mass, unfiltered by dust or gas. They could pass unhindered through matter that would block or scatter ordinary light. Each detection since has added a new voice to this cosmic symphony. Dozens of mergers between black holes have now been observed, their signals combining into a catalogue of space-time's deepest rumbles. Every one of them tells a story about where black holes form, how big they can grow, and how they dance before merging. Some of these events have involved black holes far more massive than expected, forcing theorists to rethink how such systems arise. But the most dramatic moment came in August 2017, when detectors caught a different kind of signal, longer, more complex, and followed by light. The wave pattern showed two neutron stars, the ultra-dense remnants of massive stars, spiraling together. Within seconds, telescopes across the planet swiveled toward the patch of sky where the signal came from. Observatories detected a burst of gamma rays, followed by visible light, X-rays, radio waves, and infrared emission. For the first time, scientists had witnessed the same event through both gravitational waves and electromagnetic radiation, a perfect example of multi-messenger astronomy. The universe had spoken in two languages at once, confirming that neutron star mergers produce short gamma-ray bursts and forging heavy elements in the process. The faint afterglow, known as a kilonova, revealed the birth of gold, platinum and other precious metals created in the intense nuclear stew of the collision. This single event, catalogued as GW 170817, transformed astrophysics. It provided a new way to measure cosmic distances, confirmed theories of element formation, and offered an independent test of the speed of gravity, which, it turns out, matches the speed of light almost exactly. Even more striking was the precision. The initial gravitational wave detection localized the source to within a patch of sky about 30 square degrees, and follow-up observations narrowed it to a specific galaxy, 130 million light-years away. Localization is a crucial part of this new science, the ability to pinpoint where a signal originates. With only one detector, direction is impossible to determine. The wave could have come from anywhere. But with 2 and now 3 and more, scientists can triangulate the source much like ears detecting the direction of a sound. Each observatory records the signal at a slightly different time, and those delays allow astronomers to map the source across the sky. Today, LIGO operates in concert with Virgo in Italy and Kagra in Japan, forming a global network of gravitational wave observatories. Together they can pinpoint cosmic events with increasing accuracy. In the next decade, additional detectors, both on Earth and in space, will join them. The European Space Agency's LISA mission, planned for the 2030s, will place 3 spacecraft millions of kilometers apart in orbit around the Sun, sensitive to much longer wavelengths. LISA will be able to detect slow, massive mergers and even the gentle gravitational murmurs of orbiting white dwarfs. These instruments will turn gravitational wave astronomy from a novelty into a mainstream discipline, adding a new sense to our exploration of the cosmos. Just as radio astronomy revealed pulsars and cosmic background radiation, gravitational waves promise to unveil hidden phenomena, colliding supermassive black holes, perhaps even the tremors from the universe's birth. The beauty of this new way of observing lies in its directness. Gravitational waves don't tell us how something looks, they tell us how it moves. They carry the imprint of motion itself, encoded in the rhythm of space-time. Listening to them feels less like watching the cosmos, and more like hearing it breathe. Astronomy has always been about extending the senses. First the eye, then the telescope, then instruments that capture forms of light our eyes can't see. Gravitational waves extend that progression into the realm of touch, a sensitivity to the subtle trembling of the universe itself. With each detection, we're not just seeing deeper into space, we're feeling the ripples of cosmic events as they unfold. From Einstein's equations to the delicate chirp of merging stars, gravitational wave astronomy has turned a mathematical prediction into an entirely new sense, a way of listening to the cosmos. And with this new ability, we can begin to understand how discovery truly happens, not through any single instrument or observation, but through the way the universe keeps surprising us, again and again. Astronomy might look serene from the outside, a quiet figure under the stars peering through a telescope, but in reality, it's a field built on planning, mathematics, and endless data. Behind every stunning image or headline-grabbing discovery are hundreds of hours of preparation, debate, coding, and careful skepticism. The universe doesn't hand over its secrets easily. Astronomers have to earn them, one photon at a time. The first challenge is simply getting time to observe. Modern observatories, both on Earth and in space, operate like scientific fortresses, access granted only to those who win the competition. Astronomers must write detailed proposals explaining not only what they hope to study, but why it matters, how they'll analyze the data, and why their project deserves a share of limited telescope hours. Panels of experts review these submissions, balancing novelty, feasibility, and impact. Approval rates can be as low as 10%. It's a process that forces precision. Every sentence must justify why a few hours of exposure time could change what we know about the cosmos. Once approved, the real work begins. Observing time is carefully scheduled, sometimes years in advance. Each program requires a plan, which targets to observe, how long to expose them, what instruments and filters to use, and how to handle changing conditions. On a mountain observatory, the astronomer's night starts before sunset, calibrating instruments, checking weather forecasts, and running through procedures. In space telescopes, much of that planning happens months earlier. Robotic scheduling scripts line up observations down to the second. Data collection isn't just about pointing and clicking. Every telescope, detector and sensor has its quirks. Dust on a mirror, a dead pixel on a detector, or even small temperature changes can subtly distort results. To account for this, astronomers use calibration, a process of comparing measurements against known standards to correct for instrumental and environmental effects. They might record the brightness of standard stars, take dark frames to measure electronic noise, or flat fields to even out detector sensitivity. Without calibration, even the sharpest image can mislead. Once the observations are made, the raw data hardly resemble the stunning pictures seen in the media. Most telescope outputs are just arrays of numbers, counts of photons per pixel. Transforming those numbers into something meaningful requires data pipelines, computer programs designed to clean, align, and process information into usable form. For radio astronomers, this can mean stitching together signals from dozens of dishes. For optical astronomers, removing cosmic ray hits or background glow. For space missions, combining exposures taken days or weeks apart. Then comes analysis, the detective work. Astronomers write code to extract patterns, measure velocities, fit models, and test hypotheses. In many ways, a modern astronomer is as much a programmer as an observer. They live inside databases and archives, comparing new findings with decades of accumulated measurements. The Sloan Digital Sky Survey, for example, has mapped hundreds of millions of celestial objects, and new discoveries often come not from a single night of observing, but from trawling through this digital ocean. The next breakthrough might already be sitting in the data, waiting for the right algorithm to notice it. Replication is the heartbeat of the field. A finding isn't truly accepted until others can reproduce it. Independent teams reanalyze data, apply different methods, or use other instruments to confirm or challenge results. Sometimes, what looks like a breakthrough turns out to be an illusion caused by subtle biases. Astronomers call these systematic errors, consistent distortions that can mimic or hide real signals. It might be a faint reflection in a camera lens, a miscalibrated sensor, or even the way the data were processed. Learning to recognize and eliminate these errors is one of the quiet arts of astronomy. This cautious attitude explains why extraordinary claims take time to settle. When the first exoplanet detections were announced in the 1990s, many astronomers hesitated. Had someone accounted for stellar variability? When the first gravitational wave signal appeared, teams spent months confirming it wasn't an instrumental glitch. The scientific method moves slowly, not out of doubt in discovery, but out of respect for truth. Different projects require different approaches. Some are surveys, broad systematic sweeps of the sky designed to collect data on as many objects as possible. Surveys reveal the big picture, how galaxies cluster, how stars vary, how transient events flare and fade. Others are targeted observations, focusing deeply on one object or region. The two strategies complement each other. Surveys discover, and pointed observations explain. Large surveys like Gaia, Pan-STARRS, and the upcoming Vera Rubin Observatory's Legacy Survey of Space and Time are revolutionizing the field. They scan the sky repeatedly, capturing billions of stars and galaxies, watching for anything that changes. Every night they produce terabytes of data, far more than any human could sift through manually. This has led to one of astronomy's most exciting developments: citizen science. Citizen science projects invite the public to help classify and analyze data. Websites like Galaxy Zoo let volunteers sort galaxies by shape, a task human eyes still outperform algorithms at. Others track light curves from variable stars or search for signs of exoplanet transits. These collaborations have led to genuine discoveries, new planets, rare types of galaxies, even previously unknown supernovae. They also connect people to the process of discovery, turning the night sky into a shared endeavour rather than a distant spectacle. Astronomers today often spend more time in front of computer screens and telescopes, but the romance of the night sky remains. Observatories on remote mountaintops and space telescopes like Hubble and James Webb are extensions of our senses, seeing what no human eye could directly perceive. Each image, spectrum, or signal represents layers of effort. Proposals written in hope, code written in frustration, calibrations repeated until perfect. What might look like a photograph of a nebula is actually a triumph of teamwork. engineers maintaining delicate optics, programmers processing data, analysts interpreting spectra, and theorists linking patterns to physics. Every discovery is the product of a chain of patience stretching across continents and years. Yet despite all this precision, uncertainty is an essential part of the craft. Astronomers embrace error bars and probabilities. They quantify their ignorance as carefully as their knowledge. That's because the universe is subtle. It rarely gives simple answers, but with enough data and persistence, it offers hints that lead to deeper understanding. In the end, astronomy isn't just about observing. It's about listening carefully to noise until it starts to sing. The process can feel painstaking, but it's what turns wonder into knowledge. And the people doing this work, often unseen behind the telescopes and code, are driven by the same ancient curiosity that made early humans look up and wonder where they were in the vast dark. All of this effort, from proposals to data pipelines, from volunteers clicking galaxies to scientists calibrating sensors, builds toward a single goal: to understand what's out there and why it matters. Because every measurement, every small correction, every long night of observation adds one more brushstroke to humanity's ever-growing portrait of the universe. A picture that is far from finished, but more beautiful with every discovery. If astronomy teaches anything, it's that discovery is never finished. Every question answered opens a dozen more, each more intricate than the last. The night sky may look still, but our tools for exploring it are evolving faster than at any point in history. What lies ahead is not just deeper understanding, but entirely new ways of perceiving the cosmos. In the coming decades, a new generation of observatories will transform how we see the universe. On Earth, telescopes of unprecedented size are nearing completion. The giant Magellan telescope in Chile, with its 7 enormous mirrors acting together, will gather light more than 10 times better than the Hubble Space Telescope. The 30-metre telescope and the European Extremely Large Telescope will follow, equipped with adaptive optic systems capable of correcting for the blurring effects of the atmosphere. With these instruments, astronomers will be able to study individual stars in distant galaxies, probe the atmospheres of nearby exoplanets, and watch the birthplaces of stars with clarity once thought impossible. Meanwhile, in the realm of radio astronomy, the Square Kilometre Array, or SCAR, is beginning to take shape across South Africa and Australia. When complete, it will be the largest radio observatory ever built, using thousands of antennas spread over continents to detect faint signals from the earliest epochs of the universe. It will trace the cosmic dawn, the era when the first stars and galaxies lit up the darkness, and map the hydrogen that filled space long before galaxies formed. The SCAR will also monitor pulsars with exquisite precision, potentially revealing gravitational waves on scales larger than those detectable by LIGO. Closer to home, the Virasi-Rubin Observatory will open its eyes to the changing sky. Its legacy survey of space and time will photograph the entire visible sky every few nights for 10 years, capturing billions of stars, galaxies, and transient events. This new approach, called time-domain astronomy, focuses not on static pictures, but on motion and change. It will catch supernovae in their first hours, track near-Earth asteroids, and even spot distant objects in the outer solar system. In the process, it will generate more data than all previous astronomical surveys combined. In space, even grander missions are on the horizon. The James Webb Space Telescope has already begun to peer back toward the first galaxies, but successors are being planned to go further. NASA's Nancy Grace Roman Space Telescope will conduct wide-field surveys, studying dark energy and searching for exoplanets through gravitational microlensing. Farther in the future, missions like LUVOIR or HABEX, Concepts for massive space telescopes with mirrors many times larger than Hubble's could directly image Earth-like planets around other stars and analyze their atmospheres for the faint chemical fingerprints of life. These instruments will push us from detecting worlds to characterizing them, turning dots of light into tangible places with climates and chemistry. Gravitational wave astronomy is also poised for expansion. Upgraded detectors on Earth and future observatories in space, such as the Laser Interferometer Space Antenna (LISA), will tune in to lower frequency waves from supermassive black hole mergers. These slow, deep vibrations will reveal how galaxies grow and evolve, tracing the assembly of structure over cosmic time. Together, electromagnetic and gravitational observatories will create a multi-messenger network that listens to the universe in stereo: light, sound, and everything in between. Each of these instruments will help tackle the most profound open questions in physics. What is dark matter, the invisible scaffolding that holds galaxies together? What is dark energy, the force driving cosmic acceleration? Are there particles or fields we haven't yet discovered that shape the universe in unseen ways? And perhaps the most compelling of all, is life common, or is Earth an exception in an otherwise silent cosmos? The search for life beyond our planet will soon move from speculation to measurement. Next-generation telescopes will examine the spectra of exoplanet atmospheres, looking for telltale combinations of gases such as oxygen, methane, and carbon dioxide, indicators that something dynamic is happening. Future missions may even study planetary weather patterns or surface reflections that hint at oceans or vegetation. The first confirmation of life beyond Earth, even if microbial, would be the most profound discovery in human history, reshaping philosophy, theology, and science alike. Yet astronomy's value isn't only in its grand mysteries. The technologies developed to explore the universe find their way into everyday life. The precision optics, sensors, and data algorithms that power telescopes have revolutionized medicine, communications, and environmental monitoring. Satellite imaging, GPS navigation, and climate models all owe their accuracy to techniques refined for astronomical observation. Even the CCD detectors in smartphone cameras trace their lineage to astronomy labs. Perhaps more importantly, astronomy gives context. It reminds us that Earth is not the center of anything, not the universe, not even our own solar system's attention. Seeing the fragility of our planet against the dark backdrop of space reframes how we think about climate and responsibility. From orbit, Earth is just a thin shell of air and water wrapped around a small rocky sphere. Every storm, forest, and living creature exist within that faint glowing film. The cosmic perspective doesn't diminish human life, it magnifies its rarity. There's also something deeply human in the pursuit itself. Astronomy unites nations and generations, requiring patience, collaboration, and shared curiosity. A telescope built on one continent collects light that is analysed on another and shared with everyone. It's science at its most collective, a global conversation about where we come from and what we're part of. Looking ahead, astronomy will become more open than ever before. Data archives are now public by design, allowing researchers, students, and enthusiasts anywhere to contribute. Citizen scientists already help classify galaxies and identify exoplanet signals. In the future, artificial intelligence and human intuition will work side by side to sift through the endless flow of cosmic information. The night sky will no longer belong to specialists alone. It will be a shared laboratory. It's easy to think of these projects as technical achievements, but at their heart they continue a story that began long before telescopes. The story of people standing under the stars and wondering. We're still asking the same questions. Where did this all come from? What holds it together? Are we alone? The difference now is that we have the tools to start answering them. As the next wave of observatories comes online and the universe reveals more of itself, astronomy will remain what it has always been: a gentle, humbling pursuit of perspective. The discoveries ahead will change details, but not the essence of why we look up. Because in every era, from ancient stargazers to space-age scientists, the impulse behind it all is the same: to understand our place in the vastness above. And perhaps, in returning to that question, what is astronomy? We find that the answer hasn't changed much at all. It's simply the art of paying attention to the universe, patiently, precisely, and with wonder. The night sky always feels a little different once you understand it. What used to look like scattered lights now makes sense, a pattern you can read. The stars that seemed random fall into constellations that mark the seasons. The Milky Way becomes not a hazy stripe, but the edge of our own galaxy. Even the faint moving points of light have names and purposes. After spending time with astronomy, the sky turns from decoration into geography. We've gone from ancient sky watchers marking star positions on stone to telescopes that can see the birth of galaxies billions of light years away. But through all that progress, the core idea has never really changed. Astronomy is careful noticing, not just by one person, but by many people comparing what they see, checking it, and improving it. One person spots a dim star that seems to move. Another measures its spectrum. A third writes software to confirm it's real. When that work is shared, the private act of looking becomes collective understanding. Most of what once sounded abstract now feels straightforward. The sky can be mapped and measured like any landscape. Light carries information about temperature, composition, and motion. Telescopes are just bigger, steadier eyes that collect more light and focus it better. Distance can be worked out through geometry and brightness. Gravity explains motion, and time runs differently depending on where you stand. Stars form, shine, and die. Galaxies build structure and evolve. The universe itself expands and cools. These are no longer distant facts. They're part of a picture you can now hold in your mind. Astronomy rewards patience more than memory. It isn't about knowing every number or formula. It's about seeing patterns, waiting for repetition, and understanding what changes. The same constellations shift slowly across the seasons. The moon waxes and wanes on a schedule so steady it guided the first calendars. Meteors appear and fade, but their trails return each year as Earth crosses the same debris stream. Astronomers rely on that rhythm, and so can you. It's proof that even in something as vast as the universe, consistency exists. Thank you for spending part of your evening here. There are many ways to unwind at the end of the day, and you chose to listen and think about the sky, something most people rarely stop to notice. If this helped you relax or spark some curiosity, a like or subscribe really does help this small channel reach others who enjoy learning this way. And if you're already subscribed, thank you. Your support is what allows these calm explorations to keep going. Astronomy has always been more than just science. It gives perspective. Seeing how thin Earth's atmosphere is, or how fragile its balance seems compared to the emptiness beyond, quietly changes how we think about home. The same physics that shapes distant galaxies also shapes our weather and tides. The light that left a star before human civilization began is reaching your eyes right now. That connection makes the vastness of space feel a little more personal. If you step outside later, try to find one familiar object. A bright star, a planet, or a cluster you can name. Think for a second about what you now know about it. How far away it is, what kind of light it gives off, maybe what stage of life it's in. Then just look. That simple act, connecting knowledge with observation, is the essence of astronomy. It's also what makes it worth continuing. The more we look, the more clearly we see how much we share. People all over the world look up at the same constellations, even if they call them by different names. If you'd like, share in the comments where you're watching from. It's always interesting to see how many different corners of the planet are under the same patch of sky tonight. When you turn off the screen and the room goes quiet, remember that the view outside hasn't changed. It's the same universe that early astronomers saw, only now you understand a little more of it. The ideas might fade from memory, but the habit of noticing stays. Every clear night offers another chance to practice it. So what is astronomy really? It isn't just data or discovery or distant galaxies. It's the ongoing habit of paying attention, of looking carefully, thinking clearly and sharing what you find. It's a way to slow down and see the bigger picture. And maybe the next time you glance up at the stars, you'll feel what countless others have felt before. Not distance, but familiarity.